Yes, ma'am.
Can you guys hear me? Okay, thank you. So we can start now, right? Or
Yes,
we
ma'am.
should wait for something. Okay, let's start. So yeah, hi everyone. Today's session, I am going to talk with you, and I think your exam time is getting closer. So do you guys having any break for study, a study break or anything else this year?
Next week.
Okay. So one of your friend has asked that Anvit, I think, yeah, asked to go over that NP problems, some of the example for NP problems and how to solve that very fair. And yeah, I think today I am going to do this. And also, if we have time, we will go over a small recapitulate of the overall course, that overview of the whole course. Okay, so I am going to share my screen. Let me know if you can see that. Yeah. Can you see my screen?
Yes, ma'am.
Yeah. Okay, so somebody can volunteer for what is P problem? Anyone?
Problems for which I can obtain a solution in polynomial time.
Polynomial time. Yeah. So the set of problem for which we know a polynomial time algorithm. We know how to solve this problem in polynomial time. Now here we have a list of polytime algorithm that we already know the solution how to solve these problems in polynomial time. So suppose you have asked that if two number is multiple of each other. So how can you solve this problem? Just by division, just simple division, right? So this is a polynomial time algorithm. And suppose you have asked that two number if they are relatively prime or not. You can apply Euclidean algorithm for that. And this is also a polynomial time algorithm. And what about prime check? So do you guys know that AKS algorithm?
Sir told us it exists, but like
Oh,
we don't know any
okay,
specific.
okay, fine. So yeah, so sometimes later on, maybe he will go over this topic. So for prime check, we also do have a polynomial time algorithm. Now, edit distance. I think you have solved this problem in dynamic programming, right?
Yes, ma'am.
Yeah. And L solver, that is linear equation solver, and if a graph, undirected graph is connected or not. All these problems are polytime. We know that there exists some polytime algorithm. But now, what is NP problem? So, can someone else say that? What is NP problem?
a problem for which we can verify a solution in polynomial time.
Right. So, a problem for which we can verify that problem in polynomial time. So, a problem to be in NP, we have to able to provide some certificate. We don't know who is provide that certificate, but we have to able to produce someone giving us some certificate. And using that certificate, we can verify that if that problem is we can output yes or no accordingly. Now here the idea of certificate or the idea of like verifying something, that this may be little bit some confusing. So let us look at some problem. Suppose you have the problem that you want to check if some number is composite or not. So is the problem clear? So what will be the input to that problem? You want to check if the number is composite or not. What will be the input?
The number,
Yeah, right. So the input will be some number. What can be a certificate for that? What do you think?
a boolean,
Uh, a boolean? Sorry.
a
Uh,
boolean, true or false.
Boolean forms. Okay, no, I am asking that your input is that number, and you want to know if the number is composite or not. Now, someone has to provide a certificate, right? With that certificate, you can verify if that number is composite or not, and you can give output that yes, the number is composite if the number is composite, and or you can give that output no if the number is not composite. So you want that certificate. So I am asking that what can be a certificate for that problem, for that particular problem.
Two factors.
What? Two?
Factors.
Okay. So we don't need actually two factors. Only one non-trivial factor will be sufficient, right? If someone provides only one non-trivial factor for that problem, you can just divide that number with that factor, and you can say that yeah, that number is composite. That number is not a prime number. The number is composite. But suppose your that input number was not composite at all, the number was prime, so can someone provide certificate for that number?
No.
Okay, so I think the idea of certificate and the idea of verification is clear, or is there is some problem in at least for that problem? Do you guys have any problem?
So, mom, certificate need not be the output of the algorithm.
No. They first look at this. The problem is a decision problem, right? So your input is some number, and you want to know if the number is composite or not. So what you will do? You will give output either yes or no, right? If the number is composite or not. But you don't know. You don't have any polynomial algorithm for which you can like check that number is composite, or you cannot factorize that number in polynomial time. But you want to give output. To show that problem is in NP, this is sufficient that if you can show that there exists some certificate, with that certificate you can verify that problem in polynomial time. So now if I am giving you the factor, one non-trivial factor, what you can do, you can just divide that. So you can like do the division in polynomial time, right? So what you are doing, you are dividing that thing to verify that if what I have provided you, the thing is exactly the factor of that particular input or not. You can do the whole thing in polynomial time, right?
Yes, ma'am.
So is it fine now?
So, like, certificate has nothing to do with the output, and it can be anything.
Not exactly anything. So you just think of the opposite. So if your number was prime, can someone ever can provide you that certificate? There doesn't exist any certificate, right?
Yeah.
But if the number was composite, and yeah, there exists some certificate, you can give some non-trivial factor, right? And you can verify also this thing in polynomial time. So if verifying takes exponential time, then this makes no sense. So you can verify that problem in polynomial time. Okay.
Okay, ma'am, this example is clear. This example is fine.
Okay, so yeah, let us look some more example. So do you guys know about satisfiability?
Yes, ma'am.
So yeah, you have given some Boolean formula and you want to know if there exists some truth assignment or not. So what do you guys think? If there exists any like algorithm to solve this problem, polynomial time algorithm? Okay, let's not talk about polynomial time algorithm. Any algorithm, how do we solve this problem?
Just look at all possible true and false combinations.
Okay, so yeah, so you are talking about just the way we make truth table, right?
Yeah.
So if your formula is of size n, so for every like input or every variable, you have two options, right? Either true or false, so either 0 or 1. So what you are doing that, you are trying all those 2 to the power n options for getting that output. So this thing is not polynomial, this thing is exponential. And there is a variation of this problem that we call that 3-SAT problem. So 3-SAT means in this, if you are looking at this instance, in this instance, this x1 or this x1 complement everything, any variable and complement of this variable, we call this thing as literal. And whatever thing inside that bracket, we call this thing a clause. And the whole formula is conjunctive normal form. This is basically and of or thing. So you have or between this clause and uh, outside. Now what you want to know that if there exists some truth assignment or not. 3 satisfiability problem is your every clause will contain exactly 3 literal. So here we have this instance. This is only a 3 set problem. So 3 set problem is just a variation of satisfiability problem. Now, we don't know any polynomial time algorithm, but what do you think? What can be a certificate for this problem? Anyone? What do you think?
Mm, a list of Boolean values.
A list of boolean values. So yeah, someone knows that these someone gives you a list of boolean values. So not just a list of boolean values. The certificate is that exactly the assignment, truth assignment. You don't know who is providing you that certificate, how he is going to find that assignment. You don't know that, but yeah, someone if provides you that certificate, that he is saying that this is a truth assignment of your function, then you can verify this in polynomial time, right?
Right.
Yeah. So this is the main idea. But now suppose that your whatever formula you have taken, that doesn't have any truth assignment, then whoever is providing you that certificate, he cannot produce a certificate for you, right?
Yes, ma'am.
Oh, so this is the overall
Ma'am, can you
concept.
repeat the last line?
Okay, so here what he was asking before, that certificate can be anything. Like certificate can be anything means someone is giving you a just a list of truth values. Certificate is not like that. Someone giving you the exactly truth assignment, like exactly the truth assignment. How they are producing that truth assignment, you don't know, but they are saying that this thing is truth assignment for your boolean formula. So you can verify, just put that values in your formula and verify that yeah, this formula is basically a truth assignment for my formula, and you can say yes, right? But suppose that your formula doesn't have any truth assignment at all. So can someone who was producing you the certificate, can they give you that certificate? Then they won't be able to produce any certificate for you, right?
Yes, ma'am.
Yeah, so is this problem is fine?
Yes, ma'am.
Yes,
But
ma'am.
how do I determine what a certificate for a particular problem is? Or can there be any certificate which can be verified in polynomial time?
Oh, exactly not. I think no. You are just you're messing up things. No, not like that. Yeah, certificate is like that. You don't know how to solve this problem, okay? But I am giving you some solution. You have to verify that. But what kind of solution you can verify? Like what can be the solution? This is a problem. So suppose here, uh, you have that problem, that boolean problem, and I am saying that certificate is an assignment of truth values. So, uh, if I am not giving you the truth values, instead of that I am giving you the whole truth table. So in that truth table, of course there is an assignment of truth values for that your function, right? So if you are verifying the whole truth table, you of course know something about that. But this is you cannot verify that whole truth table in polynomial time, right?
Yes, ma'am.
And also the certificate I have provided you. So I am saying that this certificate is the whole truth table. The certificate is not also a polynomial size certificate, right?
Sorry, could you repeat yourself?
Yeah. So here what we are saying that the certificate can be a truth assignment for your function. So whatever I am giving you, I am giving some truth values of boolean variables. So I am saying that set up x1 equal to true, x2 equal to true, x3 equal to false, and like that, right? So instead of doing that, what if I have given you the whole truth table? I'm saying that try for x1 equal to true, x2 equal to true, and also try for x1 equal to false, that option. So I have given you all that options. I am saying
That is fine. That can't be verified in polynomial time, I
right,
agree.
right. Yeah, and the certificate is also not a polynomial size of certificate, right? So whatever I am providing you, that thing is also exponential. The certificate size is also exponential if I am giving you the whole truth table. Is
Yes,
this
ma'am.
fine? Yeah. So certificate has to be like in polynomial size, and also certificate is kind of uh, verifier that like yeah, you have some verifier that you are using that certificate. You are using that certificate to use that verifier and to say that if the value is like if you can give the output true or false.
So, like, if I have a decision problem,
Actually, in the NP world, whatever problem we are like, we are going to say that that thing is NP. Every problem is decision problem, right? I think
yeah, they can be converted to a decision problem. I agree.
yeah.
Basically, my doubt was that the certificate has to be the output of the problem, which I now realize that is not correct.
No, no, no,
Because,
not at all. Yeah, yeah,
yeah, if that were true, then any decision problem would have to be a P problem.
yeah, yeah, yeah. No, 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 that's not at all. So if you can give that output in polynomial time, then why are you talking about like we are not going to divide that problem in P, NP or that things, right? So
Right.
then things become polynomial. The certificate is something else. So someone else providing you that certificate, and whatever you are doing, you are just verifying things, and you are saying that that problem is in NP, but you don't know how to provide that certificate, like how to produce that certificate. This job is doing someone else for you. Your job is only to verify. And whenever you are like you have some problem and someone asks you to show that if that problem is in NP first, one thing is that that certificate like you know that what can be a certificate. This is fine, right? Because if you like if you know that how to verify, then you also know that what should be a certificate. You don't know how to provide that certificate, but you also know that what should be a certificate, right?
Now, like in the vertex cover problem,
Mm-hmm.
uh,
Yeah.
and say I have a decision problem that is there a vertex cover of size at most 5? So my certificate will be a set of vertices, right?
Right.
But it can also be a set of, say, it can also be like a set of edges if I can somehow reconstruct. So basically, I'm saying all of these edges
Mm-hmm.
I have connected
Mm-hmm.
with some vertices.
Okay.
But like, is that a valid certificate? Can I choose the certificate for a problem?
Okay, okay, okay. So you are asking that instead of a set of vertices, you are going to provide a set of edges.
Right. And if basically, if this thing is true, like if there is a vertex cover of size at most 5, then every edge must be included in this certificate.
But
Since
no, no, no,
every,
no. What will be the form of your certificate?
so
What the thing you are going to provide?
yeah, so if I select vertex A, so if vertex cover, if vertex A belongs to the vertex cover,
Mm-hmm.
then I add all of the edges of A to the certificate as well. And this I do for every vertex in the cover.
Okay, okay, okay. So look at this. Suppose you have a minimum vertex cover that covers every edge. Yeah, vertex cover like the definition of vertex cover saying like that, right? So what you are doing that you are providing the whole edge set in that case, right? Because your vertex cover have covered all the edges. This is fine.
Mm.
Oh,
Yeah.
so yeah. So when you are providing the whole edges, and the problem is to find out if there exists a vertex cover or like of some size. Somebody have given him some size, and this suppose the vertex cover of size k, and this vertex cover of size k has able to cover all the edges. This is fine. This can happen. So yeah, like giving providing all the edges. Can you verify that thing? So are you really providing any information about that vertex cover?
Not really. Like that's basically what I was asking. Like, can I choose the particular certificate of a problem,
Yeah, so
or
whatever
does
I think what you are doing that you are choosing some particular instance, like for some particular graph you are doing that you can suppose I am able to produce some certificate that have some other like figure that is like consisting of some other thing. But can this be true in general for all graph?
No, no.
Whatever, like I am saying right now, when your vertex cover has covered all the edges and you are providing only the edge set, like a certificate as a certificate, can your friend verify that vertex cover problem with the whole edge, like with the whole edge set?
No.
So is this fine?
Yeah, I think I didn't get it now.
Yeah. So for that, whenever someone asking you that we are talking about vertex cover problem, so you don't know what is the vertex cover or how to find that vertex cover, but you know that for what should be the certificate. So if someone provides you the vertex cover, if I am providing you the vertex cover of size k, you can verify that, right? In polynomial time.
Yes, ma'am.
This is the main goal. So
Okay, ma'am.
what about the other people? They are getting it?
Yes, ma'am.
Yes, ma'am.
Okay, okay. So yeah, we have seen satisfiability problem. Okay, here we have another problem. Hello, sorry, give me some times. There is someone playing songs outside. I have to like, yeah. Give Hello, yeah, are you guys there?
Yes, ma'am.
Sorry. Yeah. So yeah. So we have the problem that we have an undirected graph and you want to find if there exists a Hamiltonian path or not. So what should be the certificate for this problem?
A path.
A path, a Hamiltonian path, and you can just check that path in polynomial time and you can give that output, right? So this problem is NP, but you don't know how to solve this problem. Okay, I hope this is fine. So here we have a list of NP problems that, yeah, in the previous day you have already seen that all the P problems are in NP. So can you guys, someone says uh, give us idea that how to prove that every P problem is in NP?
We just find the solution and that can be used as a certificate.
Yeah. So we can just find that solution. Exactly, if you just if you want to go through the definition of NP, then what you can do that you just run the algorithm. Your algorithm doesn't care about that certificate things. Your certificate can be null, anything or anything else. You just run that algorithm to know that solution and you give output yes or no, right? You don't care about if someone is providing you the certificate or not at all. So is this fine that P problems are in NP? Hello.
Yes, ma'am.
Yeah.
Yes, ma'am.
Yeah. So here I have some like electricity issue also. There can be load setting. So that's why I thought I may got disconnected also. Now, what is NP complete problem? You know that definition, right?
Yes, ma'am.
Yeah. What is NP complete problem?
An NP hard problem, which is NP.
NP hard problem, which is an NP. And what is NP hard problem?
A problem which cannot be solved in polynomial time.
A problem which cannot be solved in polynomial. Okay. Actually, NP hard problem is the set of problem which can be polynomially reducible, like you can reduce any NP problem to that problem. So do you guys introduce to the idea of reducibility, polynomial reducibility?
Yes, ma'am.
Okay, okay. So yeah, so basically these slides should be, yeah, before that previous one, what we were looking at until now, but I have swapped that order. So here we will look at the concept of polynomial reduction. So in throughout this course, you have seen some patterns of algorithm design. One, you have seen that greedy algorithm. So in greedy algorithm, in greedy approach, what you were doing, that suppose you have some minimizing problem, you were greedily choosing the minimum among everything. When you have some maximizing problem, you are greedily choosing that maximum thing from every possible thing what you have to avail. So greedy algorithm is like kind of easy to think of, but greedy algorithm is quite tough to give the correctness for greedy algorithm. So you have seen that Prim's, Kruskal, and yeah, that thing as greedy algorithm. And divide and conquer method, you have seen merge sort, and I think many more problem, in which you are just dividing that problem in many smaller parts and you solve them parallelly. And dynamic programming, you are like doing till now, right? Duality, you also seen the concept of primal and dual, how to make a maximization problem to a minimization things for other problem and these things. And here we have the concept of reduction. So reductions means, suppose you have two problems, x and y, and your friends know how to solve that problem y in polynomial time. Now, if you can reduce that x problem in polynomial time to that y problem, and then you can ask your friend to solve that y problem for you. So the overall task you are doing in polynomial time, right? So this type of algorithm design pattern, we will say that this is polynomial reduction. Okay, let us look at some list of problems. So here we have a list of problem. So one is shortest path. We know how to solve shortest path problem, right? But do you know how to solve longest path in a graph?
Are we assuming there is no cycle?
No, no, no. Just in general, you are not assuming anything. In general, you are given a graph and how to solve, like if there exists any longest path or not. Actually, probably we don't know. Uh, Similarly, when mean cut problem, you know how to solve that mean cut problem, but you don't know, these problems are similar, but one person we know how to solve in polynomial time, but for the other person we don't know if there exists some polynomial time algorithm or not. Here we are saying probably no, because we don't know polynomial time algorithm until now. But it may happen that after 10 or 20 years, some people come up with some peculiar tricks and they provide us some polynomial time algorithm for some problem that we were thinking that we cannot solve in polynomial time until now. This may happen, so we don't know about this problem, this type of problem. Like when you are looking at satisfiability, you know that how to solve two satisfiability, you can solve this thing in polynomial time, but yeah, three satisfiability becomes hard. Until now we don't know any polynomial time algorithm to solve three satisfiability. Similarly, for planar 4 colorability, this can be solved in polynomial time, but for 3 color you don't know. Again, for vertex covered, you know how to solve in bipartite graph. That question you were asking, that can I like take that think of that graph doesn't contain any cycle or not, that you were asking. So what you are doing, that you were assuming some condition, right? So when you are assuming some condition, there may happen that some problems become easier and you may solve that problem in polynomial time. Like you can see that thing in vertex cover for bipartite graph, you can solve this vertex cover problem in polynomial time, but for general graph, okay, you still don't know if there exists some problem that can solve vertex cover in polynomial time. Similarly, matching. Do you guys have seen that algorithm for matching? Hello.
Like which algorithm?
Hello.
Ma'am, which algorithm?
Yeah. So matching, for matching. Which algorithm, like algorithm to
Like,
find matching in a graph? Have you
like,
seen that?
like we just saw one in which like we can formulate as a graph problem and do it.
Yeah. Of course. So I think you have seen bipartite matching, right? How to solve bipartite matching?
Yes, ma'am.
Sir did one example in which he converted it to the network flow problem.
Yeah.
That was
Okay.
only.
Okay. So yeah, that converting problem in some other problem, you have seen this thing also. Yeah. So yeah, this is very good. Today, whatever we are like talking here to reduce that problem, some problem to other problem. This the same idea that yeah, how we can just convert one problem to another problem. And of course in polynomial time. Okay, there are no problems. For matching, we also have some polynomial time algorithm. For primality testing, we have polynomial time algorithm, that AKS algorithm. But yeah, for factorizing, you don't know any algorithm. Actually, our security system, whatever like until now, that thing is like stands over this assumption that factorization is hard problem. You cannot do factorization in polynomial time. And yeah, linear programming, we know that how to solve in polynomial time. For integer linear programming, we don't know if there exists a polynomial solver or not. Yeah,
Ma'am,
someone was talking something. Yeah.
yes, ma'am. So, say for example,
Mhm.
is X composite? We can easily see that it is an NP.
If hello,
Like the problem is X composite.
X composite.
Uh, like, like we can easily see that it is an NP.
Yeah. We can easily say that it is
Uh,
NP,
does
right?
that imply that is X prime is an NP?
X prime means
Like, does that imply that the problem is X prime? Is does that imply that it is an NP?
what is the problem? X prime. Oh, acha. Okay. So if that X's problem is prime or not, right?
Ha.
Okay, yeah, if you can reduce that factorization problem in polynomial time in that prime problem, can you do that?
No, I'm not talking about the factorization problem. I'm just saying like if we know, say some complement of the problem is an NP.
No. That complement of NP problem, there is some concept, other concept that co-NP. There come some more problems in the picture. Like don't do things like complementing something. If you want to say something, suppose you are asking that if you are in the factorization problem, and from there you can say about something that you want to comment about primality test. So for doing this, what you have to do, that you have to reduce that problem in polynomial time to primality test. You have to do this. You have to reduce things in polynomial time. Don't do that thing by complementing, because complementing things some like in some places will lead you the wrong answer, because here the complement of NP problem is P is not like that,
Okay.
because P problems are already in NP, right? So you
Uh,
cannot say that like complement of one thing is in the another set.
no. I mean, I just want to know if we can say it's in the same set. Like,
No, not
is
like, it's not also like that, because
okay.
primality testing, that thing is in P, and factorization, that thing is in P.
No, but like factorization, like I
Mhm.
mean, by complement, I don't mean factorization and say primality testing. I'm just saying like composite and prime. Like,
I understand, but these
okay.
two problems are different, right?
Huh.
So yeah, so what in the factorization, what you are doing that, so someone, you have some input and someone is providing some factor, non-trivial factor, right? And you
Mm.
like divide that factor into divided that factor, the factor is certificate for that problem. But
Yeah.
can the factor be certificate for that same certificate can certify this that like your given number, that input number is prime?
No, it can't. That's
Uh,
okay.
So you need some more certificate. Actually, what you can do that, suppose you want to check a number n, for a number n, your input was number n, you can give that from all number 2 to square root n, all the number as certificate, and that will be not a polynomial certificate, polynomial size certificate. You cannot verify also that thing in polynomial time, right?
Oh, okay. Okay.
Are you getting this? Yeah.
Yes. Yes. Yes.
Okay.
Ma'am, so
Mm-hmm.
for is X a composite number,
Mm-hmm.
we have a very obvious certificate, like one of the factors, right?
Yeah. Yeah. Yeah.
So for the problem, is X a prime number?
Hmm.
What would the certificate be?
Yeah, so when if you look at that AKS algorithm, you know that what will be the certificate. The certificate is like, yeah, rules, some like a to the power n modulo 1 something. Yeah, so there is two equation.
That's like Fermat's little theorem.
Yeah, yeah, yeah. So these two equation, that if there exists something that satisfies this and doesn't satisfy the next equation, then you can certify that. This is the primality certificate. You can do some digging up in this direction. Just look at that primality certificate. Since you guys haven't seen that AKS algorithm, I'm not going into this, but yeah, so you can give that.
Okay, so like we have two decision problems, vertex cover of size at most B and vertex cover of size at least B.
Vertex cover of size at least phi. Okay.
So for the first problem, I can just provide a vertex cover as a certificate.
Okay, so here you can see that, just notice that, so vertex cover is a minimization problem, right?
Yeah.
Yeah. So yeah, so if someone asking you about at least problem, that yeah, is there exist a vertex cover of at least k, and your graph was of your graph contains suppose n vertices. Okay, so your algorithm is always say yes, because algorithm can give output all the vertices.
Right. Okay, that would always be true.
Yeah, that will be always be true, right?
Right. So
And for some other problem also, you can think of some other problem. Yeah, so go on.
trying to relate certificates of a problem, of a decision problem.
Mm-hmm.
So a decision problem will output yes or no, right?
Yes.
So I define the corresponding decision problem as not of this decision problem.
Hmm.
So if my problem P returns true, then my problem P prime will return false.
If my P problem return true, then
Okay, I think P is a bad name because of PNP. I should probably choose M.
okay, you are talking about some two problems. Suppose these two problem is some X and Y.
Yeah, so M with some, say, graph returns yes. So M prime with the same graph will return no.
Okay.
Now say I have a certificate for the M problem and I know that M is an NP.
Okay.
Do I know that M prime is also an NP?
No. So whatever you are talking about, you are talking about completely two different problem. So for to relating to problem, you have to first like able to be reduce one instance to the for the other problem. So
But
suppose
that I've already given you. I know if M of X is yes, then M prime of X is no. I know that. This is if and only if condition.
okay, this is if and only if condition. Okay, yeah, go on.
So do I have a certificate for M prime then?
Okay, so I'm not getting your problem exactly, but I can give you some example. So suppose we are looking at that problem. Independent set and vertex cover problem. Okay. So if your graph, do you know, if everybody know about independent set and vertex cover?
Yes.
Yes, ma'am.
So yeah.
Yes, ma'am.
if one graph, if your graph have some independent set of size k, then the similar graph, same graph has vertex cover of size n minus k. Is this true?
Yes, ma'am.
So if somebody is providing an independent set for your graph, you can just give output that other set, that v minus h set, just a vertex cover for the other problem, right?
Yes.
So one problem is minimizing problem and other problem is maximizing problem. This is true.
Yeah.
So vertex cover, you want that minimum to be minimum, like minimize that, and independent set you want to know that like maximize that. This is also true. And for this, like for this case, you can reduce one problem to another problem, and you can so that like everything, the reduction and everything you can do in polynomial time, and these two problems are related with each other. You can prove it. But what you are saying that you have two different problem, and you are saying that some problem is, if for some certificate the problem will always give you true, and the other problem will always give you false, right? And you want to relate between these
Not
two.
always. Not always.
Then
For a particular input.
okay, for and
For a
but no,
particular
no, no.
input,
Then
if
you cannot say. Then you cannot say anything.
no,
You have to like always things.
sorry, I think I wasn't clear. So I mean, for all inputs x,
Mhm.
mx is equal to, if mx is equal to true, then m prime x is equal to false, and vice versa.
For all x, if mx equal to true.
And this is for all possible inputs.
Okay. Okay, and
Like,
then what you want to conclude that?
then that if m is in NP, then m prime is also in NP.
For all x, right?
Yeah, this is true for all inputs.
No, you cannot do that. Okay, let me give you some example. So you can do exactly the opposite thing, right? For all x, if you can prove that mx equal to true, if and only if always my equal to true, and vice versa, then yeah, two problems are equivalent. And if you can prove only one side, like mx equal to true, if my equal to true, then you also can say that both of the problems are in NP. So
What
whatever,
are,
yeah.
what are x and y?
Okay, oh, that x is that input.
But how is y related to x?
If you have two different problem like m and problem some m dash. So,
Yeah.
so the problem the instance of first problem, you have to reduce the instance of first problem for the second problem. This may take some time. This may there may be x may be same or x may be something different. I am just generalizing that fact. So if you want to take like give that input x in both of the problem, this is also okay.
Okay.
So you have two problems, and if you have two different problems, if some for input, for some particular input, this first problem is giving you the output true, and for that implies that second problem is also giving you that output true, then you can say that both of the problem is in NP. And if both of the problem is in NP, then you can say that both of the problem are
Yeah.
no. In this case, you cannot say that the thing is in NP. So both of the problem is NP. So the idea is here. So this is basically maintaining the hierarchy. The idea is here. You have two problems. So you somehow want to relate between these two problems. So whatever way you are relating, that doesn't matter. So you do it in polynomial time. So suppose you take an example. You have two problem m and m dash. you know that your friend can solve that m dash problem in polynomial time, or somehow, or may not be in polynomial time, and you want to use that your friend's algorithm to solve your m problem. Now you have some input x. Now this input may be directly like give you to that m dash problem, or there may be need some modifications. You do that modifications, whatever you want to do, but you only use only polynomial time. Then you call your friend, come and solve this problem. Okay, your friend solved that m dash problem in polynomial time. Now if that first problem, that problem you already have, if that, for instance, that input what you are giving in the first problem, that was true, then the input for the next problem, that has to be true. This is an if and only if condition.